Hello, everyone. My name is Francisco Castro. I recently graduated from Columbia University. And today I'm going to talk about spatial capacity planning. This is joint work with my advisors, Omar Besbes and Ilan Lobel. So the motivation behind this work is to think about how a platform or a service system that operates in a spatial environment should set a desire or target capacity or supply levels. Okay, so one example that we're going to have in mind are going to be ride-hailing systems such as Uber, Lyft, Didi, and Via. Okay, and this platform, as you all know, operates in a city, in a two-dimensional environment, matching drivers with riders that want to go from point A to point B. And in general, we can have different situations that can emerge. We can be in a situation in which we only have a few customers in the system, in which case the platform is going to provide a good quality of service because upon arrival, a customer does not have to wait to be assigned a server. At the same time, we are going to have poor utilization because we are not going to be using all the resources in the system. We can be in another situation in which we have many arrivals to a system, so many that some of them will have to wait. We're going to be offering a poor quality of service, but we're going to have great utilization. Given this trade-off, the question that we want to answer is, what is the right target number of cars that a platform should aim for? Okay, and to start thinking about this question, let me spend just one slide telling you about some basic ideas that people have used in the past to think about this type of questions for service systems that do not operate in a spatial environment. And later on, during the talk, we're going to use these ideas for our problem of capacity planning in spatial environments. So let's start with a classic multi-server system. The picture that I want you to have in mind is as a call center. We're going to have Poisson arrivals with rate lambda, exponential service time, with some in S and N servers. And for this system, we want to figure out what is the right capacity level. And people have looked at different metrics. One is the system cost, which is given by a combination of the cost of having a certain number of servers in the system plus the cost of having customers waiting. Another metric, which is going to be the focus of this talk, is the probability of having to wait to be assigned a server, which I'm going to denote by this expression over here. And I want you to know that this metric actually captures the trade-off I was talking about in the previous slide, because when this probability is close to 1, then a customer upon arrival is very likely to have to wait. Okay? And this happens only when all the servers are busy. So we have poor quality of service, but we have great utilization. And when this probability is close to 0, then upon arrival, a customer is unlikely to wait, but this only happens when some of the servers in the system are not being utilized. Okay? And exactly when this probability is strictly between 0 and 1 is when we strike a balance between these opposing forces of utilization and quality of service. Okay, so there is this classic result in queuing theory by Halfin and Witt in the early 80s that says that if you want to strike a balance, you need to set the number of servers according to this expression over here, in which the first term is a quantity known as the offer load. This is the number of servers that you will set in the system if the system was deterministic. But the system is stochastic, and in order to hedge against stochasticity, we need the orange term over here. This is a buffer term. It's a constant beta times the square root of the offer load. People in the R community refers to this expression over here as the square root safety staffing rule. Okay? So what we have here is a very good understanding of how to set the number of servers in the system to achieve a good performance in service systems that don't have a spatial component in their operation, classic service systems. But now, if we step back for a second and we compare the classic setting with the spatial setting, in terms of the time that a customer spends in the system, what we have is that in the classic one, we have, from the customer's perspective, we have waiting time plus service time. Now, in the spatial one, we have waiting time. This is the time that a customer has to wait to be assigned a driver. We have travel time, which is the time to go from point A to point B, but now we have an additional source of workload in the system, which are pickup times. This is the time that takes the driver to go from wherever the driver is to the origin location of the customer. Okay, and these pickup times add more work to the system, and they do it in a very non-trivial manner. Why? Because pickup times are state dependent. They depend on where the agents are positioned in the system, and also pickup times depend on the dispatching protocol in place. The algorithm the platform is using to match riders to drivers. Okay, so bottom line, the classic system is fundamentally different from the spatial one. The reason is because now we have spatial frictions, which are these pickup times that are adding extra workload to the system in an endogenous manner. So given this, the fundamental research question that we want to address is, how should capacity thinking be adapted to spatial environments in which now servers need to reach customers before service can start? And in particular, we would like to know whether this sort of standard rule of thumb, the square root safety staffing rule, is valid in spatial environments. So can we set the number of servers according to this expression and expect to achieve a good performance? Okay, so these are the research questions that we want to look at today. I'm gonna go super quickly over the related literature. I just want to highlight here that, so this work relates to several streams of literature in queuing theory, in staffing, state-dependent service rate systems. And then in terms of the literature on ride-hailing platforms, perhaps the closest papers to ours is this EC paper of 2017 by Castillo and co-authors, which look at the role of spatial frictions of pickup times from a pricing perspective, but in this paper we are doing it from a capacity planning perspective, okay? And this work also relates to the literature on stochastic vehicle routing, from which we borrow some tools to analyze our problem of capacity planning with spatial frictions. So this is the model I'm thinking about. We're gonna have a spatial multi-server system, so two-dimensional region with n servers. We're gonna have Poisson arrivals with rate lambda. Each arrival is gonna come with an origin and a destination. These points are gonna be independent from each other and randomly uniformly distributed in the two-dimensional region. Okay, and there's gonna be a platform that's gonna match riders to drivers using some algorithm. And once a match happens, the driver picks up the rider, and then they go to the destination of the rider. And in general, we're gonna have many, many arrivals to a system, okay? And what we want to understand is when this probability of having to wait is strictly between 0 and 1, and we're gonna look at a setting in which we're gonna scale up the number of servers in the system together with the arrival rate in the system, okay? This is known as a heavy traffic regime. What are gonna be the challenges when we study this? First, we're gonna have a large state space. For every agent, we need to keep track of their locations and system times. Then we need to think about dispatching protocols in principle. So there has to be an algorithm in place to match riders to drivers. And in principle, this could be an arbitrarily complex algorithm. And then we also have the fact that service times, because of pickup times, are an endogenous object. So given these challenges, it would be nice if we could think about a simple model of the system dynamics that captures spatial frictions given by pickup times. So to do that, in the paper, we consider this idea that we call spatial economies of scale. So I'm showing you here 3 pictures. The one on my right is a case in which we have more servers than customers. On my left, we have a case in which we have more customers than servers. And in the center, similar number of customers and servers. So now when we are in the 2 extreme cases, what happens is that there is a high supply imbalance in the system, high supply density or high demand density. In either of these cases, there is a lot of flexibility in the system, so the platform can really optimize the dispatching decisions, and as a consequence, pickup times can be small compared to travel times. Whereas when we are in the case in the center, there is not a lot of flexibility in the system, and so pickup times are going to be similar to travel times. Now, if I were to draw a plot of this relationship and telling you with words, it would look something like this. So in the horizontal axis, I have the number of customers in the system. N is the number of servers. On the vertical axis, I have the average service time given by pickup times plus travel time. Now, what I just said is that if we have high supply density or high demand density, pickup times are going to be small, and so average service time is going to, pickup times are going to be small, and so average service time is going to be close to travel time. Whereas when we have low supply density or low demand density, pickup times are going to be high, and as a consequence, average service time is going to be close to 2 times the travel time. So this idea is what we call spatial economies of scale, and they're going to help us to think about the dynamics of the system, are going to help us to think about good dispatching protocols, and also approximations for the service rate of the system. Okay? And using this idea, we're going to come up with a simpler model of the system dynamics. Okay? And so this is how we do it. I'm going to take my spatial system, and I'm going to create a new system. This one is going to be simpler, but it's going to capture the fundamental features of the first one. And actually, we will see down the road that it's going to give a good prescription of what happens on the original system. Okay, so the way we do it is we think about the spatial system as a black box, and we think about the input and output rate of the system. The input rate is easy, it's just is the input rate from the Poisson arrival process. The output rate is a more complicated object that in particular depends on the state of the system and the dispatching protocol. So I'm going to call this quantity mu of q. We do not know much about this quantity, but what we know is that 1 over mu of q is equal to the average service time. The average service time has two components, travel time and pickup time. The travel time with this quantity we know because it's going to be proportional to the distance between 2 points in the system. The pickup time we don't really know, and in particular, this depends on the dispatching protocol, right? And this can be arbitrarily complex, so we ideally would like to simplify this, okay, to understand pickup times. And here's where we use the idea from the previous slide. We're going to focus on a dispatching algorithm that is called nearest neighbor. We focus on this algorithm because it's simple to understand, and also it's been proven in the literature that it has a good performance. It's not the best algorithm, but it does reasonably well. So this is how it works. I'm showing you two situations here, one in which we have more servers than customers. In this case, an arriving customer is going to be matched to the closest server or car, and another situation in which we have more customers than cars, and an idling car is going to be matched to the closest customer. Okay, so that's nearest neighbor, and this is nice because now we can use this idea to provide we can use this idea to provide an approximation for pickup times. So there is this result in probability theory that says that the expected minimum distance of k points to a single point scales as 1 over square root of k. Okay, and when we are doing nearest neighbor, we have a point, and we compute the minimum distance of a bunch of other points to a single point. Okay, so this is exactly what we are doing with this algorithm, and so now we can replace k by this absolute difference between the number of customers and the number of servers, and we obtain an approximation for the pickup distance, and as a consequence, an approximation for the pickup time. And now we can replace that in our expression for the service rate, for the average service time, and we end up with an approximation for the service rate of the system. Okay, so we now know the input rate, and we know an approximation for the departure rate of the system. But we still have a problem here because the system is, we still have a large state space. So we're going to take a further approximation step, and we're going to look at a Markovian approximation of the previous system, okay, an MMQN system, okay? So basically, this is going to be a queuing system with Poisson arrivals with rate lambda, and the departure rate of the system is going to be exponential, and it's going to depend on the state of the system in the way I just showed you in the previous slide. This is great. Why? Because we can actually write down the stochastic dynamics of this system, and we can use this stochastic dynamics to analyze this quantity that we want to study, this probability of having to wait. Okay, and the way we do it, we look at the fluid the fluid model of this stochastic dynamics. This is going to give us the equilibrium points, and once we have the equilibrium points, we look at the stochastic fluctuations around those equilibria, and this is going to give us a complete understanding of this quantity over here. Okay, so what are the results? So we show that the system can be stable around different operational points. There is one stable situation in which servers or cars are idling. There is another stable situation in which customers are waiting. The first one emerges because we're going to have a high supply density. The second one emerges because we have a high demand density. Okay, and this we can show this in the fluid regime. But now the thing is that the stochastic system can actually go can be either of these two equilibria, okay? And actually it can also fluctuate from one equilibria to the other. So to understand what happens, we need to understand these stochastic fluctuations, and by doing that, we get the following result. Okay, so now if we set the number of servers according to this expression, so the number of servers n is going to be equal to the offered load time plus a constant beta times the offered load to the power of alpha, with alpha larger than 2/3. So this is a case in which we have enough servers in the system. Then we can show that the limiting probability of having to wait is going to go to 0. In this case, because we have enough servers in the system, we end up in the first stable situation in which cars are idling, okay? And then we can show that if we set the number of servers according to a similar expression, but we set alpha below 2/3, then the limiting probability of having to wait is going to be equal to 1. So this is a case in which we don't have enough servers in the system, and in this case, we end up in the second stable situation in which customers are almost always waiting, okay? And from this result, what we see is that the square root safety staffing rule, this classic rule of thumb that was used in classic queuing theory, does not apply to spatial environments. In that rule, we will set alpha equal to 1/2. This will put us in the second valid point, so the limiting probability of having to wait is going to be equal to 1, and all customers almost always wait, okay? So we'll have a poor quality of service. To have a balance between quality and utilization, we need to set the number of servers according to this expression over here, in which the critical regime is going to be alpha equal to 2/3. And by setting the number of servers according to this expression here now, the limiting probability of having to wait is going to be strictly between 0 and 1. Okay, so bottom line, the classic understanding that we have from queuing theory does not apply. Alpha cannot be equal to 1/2 in spatial environments. Because we have extra workload in the system due to pickup times, we need a different scaling, which is alpha equals to 2/3. Okay, and the way we proved that the limiting probability is strictly between 0 and 1, we show that the system oscillates from one equilibrium to the other. We can also argue that this is the right scaling when we are looking at, when we want to minimize the total system cost. Okay, so we can run some simulations, and what I want to show you here is that when we set the number of servers according to our previous theorem, actually what happens, so the picture on my left corresponds to a sample path on my right to a sample path of the Markovian system, on my left to a sample path of the true system that I wanted to approximate. And we can see here basically that both systems oscillate around two equilibria. One equilibria is a state of the world where customers are waiting. The other one is a state of the world where servers are idling. Okay, so what we see here is actually the equilibria prescribed by the Markovian system actually provide a very good approximation for what happens in the true system. Okay, so the approximation we develop is capturing the fundamental features and behavior of the true system. And I'm going to leave you with the takeaways, but I just want to stress the fact that what we show in this paper is that the classic rule of thumb, the square root safety staffing rule, does not apply to spatial environments. In spatial environments, now we need new rule of thumbs, and for the model I presented today, is going to be this expression over here, where we replace alpha equal to 1/2 by alpha equal to 2/3. Thank you. Yes, so the assumption is important. That assumption is important. So the assumption was that every origin destination pairs are independent and randomly uniformly distributed in this region. Okay, so you can think about this as a best case scenario. Okay, so now you can, and I have it here, so you can try to think about scenarios where you have spatial demand patterns. So origin and destination pairs follow some spatial pattern, and in that case, you are going to need more. It's not going to be 2/3, it's going to be a little bit more. Okay. Yes, so if you do 3 dimensions, it's d over d plus 1. I think so. Yeah. Yeah, so you can do more dimensions.